Before I jump into this one, I'll introduce myself. My name is David Cahuth. I also go by a number 25. You might say, well, where does that come from? Well, the thing is that I have a long history of racing, and that was the number on my car back in 1988 when New Holland asked me to change my initials. I was working in engineering at the time, and we used to assign part numbers, and you had to put your initials down, and there was somebody else that had the same initials as I did working in engineering. So they came to us and they said, one of you guys has to change your initials. So I volunteered to go to 25. The reason I tell that story at the beginning of all my presentations is it's a qualifier. If I could qualify myself with our salesmen, and they know that I have this racing background, why, when I start talking about emissions on high horsepower diesel engines, well then they kind of tend to believe what I'm telling them. Okay? I have a confession to make to you people right here. Back when I was at Penn State studying mechanical engineering, I was in the library. I was supposed to be studying for finals, but a lot of times I found myself reading Successful Farming magazine. I told that to the last group that was in here, and they looked at me and they said, never heard of it. So you might want to tell some of your colleagues, you in particular, that this guy's really okay. So let's jump into this thing.
I'll have a word with the rest of them.
There you go. Right. We're going to be looking at emissions technology here, and once again, before I get into that in detail, I want to set the stage a little bit. People are resistant to change overall. So one of the things that I've encountered as I've been teaching emissions for the last 3 years is a reluctance to change. People asking the question, why do we have to do this? So if we just skip down memory lane a little bit and look at things like Pittsburgh at the turn of the last century, we might have seen something like this. Or coming a little bit closer to today, 1948 in Denora, Pennsylvania, this was noon on October 29th. They had to turn their streetlights on just to see in that town. We were very harmful and wasteful when it came to Mother Earth. But what we have to realize is that we have to take care of Mother Earth if we want her to take care of us. It doesn't matter who the manufacturer is, it doesn't matter what continent we're in. We're talking about quality of life here. Now to look at the world today, we have 7 billion people on Mother Earth. And if we look at the UN's timeline with the population of the Earth, here we are today, we have 7 billion people. If we go back to 1967, there were 3.5 billion people on Mother Earth. So in that time frame, we've doubled the population. 1967 wasn't that long ago. I can remember the Beatles releasing Sgt. Pepper's Lonely Hearts Club Band. Now the vision of FPT is to be a game changer in powering the future. What's the best solution to these emissions? Well, before we get into that in detail, I want to qualify FPT a little bit. If we look at the year 2012 on worldwide engine production for diesels, between 2.2 and 20 liters, we see that Fiat Powertrain Technologies ranked 5th in the world. If we concentrate on Tier 3 and Tier 4A engines, the ones with the latest technology for emissions, Fiat Powertrain Technologies was 3rd in the world at 450,000 units. The significance of this slide is to say that FPT is one of the majors. They're a heavyweight in diesel production worldwide. If we look at, real quick at the history of Fiat, Iveco, and FPT and engine development. They had their first industrial engine way back in 1903. Fast forward to 1999, and they applied the first common rail fuel injection systems onto an industrial engine in that year. This common rail fuel injection is very important to the technologies that are being developed for emissions today. In 2005, Iveco released SCR-only technologies onto the roads of Europe in high horsepower diesel engines. That's the same SCR technology that's the base of our solution today for Tier 4B, what we term high ESCR, or high efficiency selective catalytic reduction. The goal with high ESCR is to keep it simple, keep the solution simple, and get the results that we need. The target was to design engines for power, efficiency, and performance while meeting strict emissions regulations for particulate matter and oxides of nitrogen. Since the tier formula came into effect in 1996, there's been a big reduction in 2 components of the exhaust, the particulate matter and the oxides of nitrogen. This graph here shows how we've been driving those results down towards 0 till we get down into the lower left-hand corner of this graph in 2014. Moving from Tier 4A to Tier 4B, let's see, Tier 4A to Tier 4B, there was no reduction in the particulate matter. This line stayed constant. but there was an 80% reduction in the oxides of nitrogen. So on the x-axis, we had to move from this position over to here to get into the bottom corner right there. So that's significantly improving the position of the environment. Real quick review of these two emissions components. We have particulate matter, or PM. This is unburned hydrocarbons that's caused by incomplete combustion in the cylinder. And then we have the oxides of nitrogen, or nitrogen oxides, commonly abbreviated NO sub X. These are nasties that go up and attack ozone and help to contribute to acid rain. So these are the two primary components that the emissions regulations are looking at. Now, if we look inside the engine, everything that happens in there with these components is based on the combustion temperature within the cylinder. If we have high combustion temperatures, we burn more of the available fuel, we produce less unburned hydrocarbons, which is particulate matter, so that is decreased. The nitrogen and the oxygen atoms want to bond at high temperatures. So if we have high temperature combustion, we're going to form these oxides of nitrogen. On the flip side, if we can lower the combustion temperature, we're going to increase more unburned hydrocarbons, more particulate matter. That increases. But the oxygen and the nitrogens don't want to bond together, so we decrease the amount of oxides of nitrogen that are formed. Some manufacturers choose to use this as the basis for their EGR, or exhaust gas recirculation technology. The reason for that is that by recirculating exhaust gas back into the engine, we lower combustion temperature. The reason for that is that the exhaust gas has already been burnt. It's basically inert. And if we put that back into the cylinder, what we do is we displace oxygen and we, in effect, detune the engine a little bit. And that will lower this temperature, and it allows us to set up this scenario right here. Whichever side that you pick, whatever component comes out as the increase, that needs to be dealt with post-combustion with an after-treatment system. Up until Tier 3, all the emissions were done inside the engine itself. At Tier 4A, with the much more stringent emissions requirements, all manufacturers had to go to an after-treatment type system. That was referred to as an ATS. For the SCR people, we have the high oxides of nitrogen. We deal with that chemically post-combustion. And for the EGR-based systems, they have high particulate matter, which is dealt with post-combustion with a diesel particulate filter. That's abbreviated DPF in the industry. A quick synopsis here on this is selective catalytic reduction is a simple system that treats the exhaust gas with urea, and the urea is the carrier of the ammonia, that is the working component. That eliminates pollutants, allows the maximization of engine power through a more complete burning of the available fuel. That's SCR. On the other side, we have cool exhaust gas recirculation with a diesel particulate filter, where we recirculate exhaust gas back into the engine. And the purpose of that is to reduce the peak combustion temperature, and that will limit the oxides of nitrogen that are formed. But this will also sacrifice engine performance and form more particulate matter. So those are the two strategies that manufacturers are using. Now, if we look at EGR rate, how much of the exhaust gas is recirculated in the engine, we look at that rate relative to the oxides of nitrogen produced and the fuel that the engine will consume. If we come over here to 0 on the exhaust gas recirculation, the engines will produce about 0.825 grams per kilowatt hour on average. To get to Tier 3 levels, that limit had to come down to about 4.4 grams per kilowatt hour. If we follow our oxides of nitrogen line on here, we see that we hit 4.4 grams per kilowatt hour at about a 10% exhaust gas recirculation rate. For Tier 3, all manufacturers of high horsepower engines were using a strategy like that. Even New Holland, because you could meet the regulations. The fuel consumption going from 0 gas recirculation to 10% hardly changed at all. Okay, so there was no real gain in going or looking for another solution at that point. To get to Tier 4A, the reduction in oxides of nitrogen had to get down to below 0.1 gram per kilowatt hour. So if we follow the line of oxides of nitrogen, we see that we have to get to about a 30% exhaust gas recirculation rate to meet Tier 4A requirements for oxides of nitrogen. Some manufacturers stayed with EGR at that rate, but they were starting to give up some of their fuel efficiency because If you detune an engine, you have to put more fuel in to get the same amount of power out. So that's what was happening there. New Holland got away from EGR at that point and adopted SCR only. To get to Tier 4B with that further 80% reduction in oxides of nitrogen, you have to get down to below 0.025 grams per kilowatt hour. That crosses the 40% line. But at 40% exhaust gas recirculation, with an engine detuned to that extent, we see that the fuel consumption rises dramatically. So today, nobody's using a 40% EGR rate because it would price you right out of the field. Let's take another look at this. We're going to look at the particulate matter produced and the oxides of nitrogen in these engines. If we go back to 2002 with Tier 2 engines, where everything was done inside the engine, we produced high amounts of particulate matter and high amounts of oxides of nitrogen. If we graph that out, we got to this portion of the graph right there. Moving from Tier 2, advancing, we had improvements in combustion efficiency due to the high-pressure common rail systems that most people are using. Also fuel mapping, which got us down into this realm on the chart. We reduced the particulate matter, but we increased the oxides of nitrogen. Now that's inside the engine. What the exhaust gas recirculation crowd decided to do was, while we're still in the engine, they were going to play with the mixture, recirculate their exhaust gas to cool that combustion temperature down, form less oxides of nitrogen, but form more particulate matter. So that arrow climbs, and we get to a point about here. Now for Tier 4A, they had to go to an after-treatment system to clean up the particulate matter, and they did that with a diesel particulate filter to mechanically filter the particulate matter out of the exhaust flow. And that got them down here into the Tier 4A realm on the chart. Now to get to Tier 4B, where we have to reduce the oxides of nitrogen even farther, there are two theoretical ways to do that. One would be to start back here at this point, use exhaust gas recirculation, but continue to do it up to about a 40% rate, which would get you here with high particulate matter, and then filter down to get into the allowable emissions regulation. The problem with this, as we saw in that previous chart, was that the fuel consumption starts to go up by about 20%. So nobody's doing that. They're stopping here at about that 30. They're filtering their exhaust flow to take care of the particulate matter, but now they have to make a jump in the reduction of oxides of nitrogen. And the way they do that is they add selective catalytic reduction to their systems to mechanically take care of the oxides of nitrogen. Hence, we have an EGR plus SCR hybrid system. If we look at SCR only, we would have the same starting point at Tier 2. Improved combustion got us down here. But the route that FPT and New Holland decided to take back a few years ago was to use selective catalytic reduction and treat the oxides of nitrogen chemically to reduce the oxides of nitrogen and get into the Tier 4A realm right there. Now, if the goal moving from Tier 4A to Tier 4B is to continue the reduction in oxides of nitrogen, how might we do that? Continue to do the same thing, but do more of it, and do it more efficiently. That's where the term high ESCR, or high efficiency selective catalytic reduction, comes in. If we look at some diagrams of real-world examples of these two systems side by side, the EcoBlue high ESCR on the left, we have a basic engine with a cooling package on the engine. We have a turbocharger here to help make power. We have a diesel oxidation catalyst and an SCR chamber. Diesel exhaust fluid tank, controller, and supply line. So what we have here basically is an engine that's set up to make power with an after-treatment system on it to handle the oxides of nitrogen. If we jump over here to the CEGR-based solution, we have a basic engine with a cooling package on the engine, but then we have this other little circuit here which says EGR cooler. Well, before we put that hot exhaust gas back into the engine, we need to cool it off, otherwise it's going to have thermal consequences on the density of the charge going into the engine, and we would detune it even farther. Now we're already detuning it by putting the inert gas or the exhaust gas in there to displace oxygen, so we have to preserve the density of that charge to make some power. There's a primary turbocharger on those engines, and because the engine's detuned, what some manufacturers have done is put a secondary turbocharger on there to push more of an intake charge into the engine. And some of the manufacturers have also gone to more displacement. Because if you have a 500 horsepower engine and you detune it, you still want to get 500 horsepower out of it. The only way you can do that is put more stuff in the engine or make the engine bigger. So here we have some complexity on the turbochargers. The particulate matter that they generate was taken care of by the diesel particulate filter, but then to move to Tier 4B, to further reduce the oxides of nitrogen, they had to add an SCR system onto that engine system. When they added the SCR chamber, they had to add the diesel exhaust fluid tank controllers and lines. So over here we have a very, very complex hybrid system that's achieving the same results as the high ESCR over here on this side. So if we look at them from a complexity standpoint, this one is the simple, the smart solution. Another way to view this is that if you have a complex system like that, there's more chance of failure out in the field where it really matters. Now, we're going to take a look at the chemistry of the SCR very basically. I mean, we could spend all week on this if you really wanted to. But we basically have our oxides of nitrogen in the exhaust flow. We're injecting urea, which is a carrier of NH3, ammonia. Those constituents go into the SCR catalyst, where they're broken down into elemental nitrogen, hydrogen, and oxygen, and then they reform as nitrogen gas and water vapor, and that's what's evacuated to the atmosphere. So that's the chemical process that's involved with our SCR. If we look at the system itself, comparing Tier 4A to Tier 4B, we've added some components onto this to make this whole thing work better. We have the same basic engine here cranking out power. On the SCR chamber itself, we've changed the catalyst inside there to be more efficient. The change to the new catalyst also allows us to run the engine hotter, which means we can get more power out of it from the fuel that we put in. The efficiency of the SCR chamber is dependent on its temperature. On cold start, okay, we need to get this thing up to operating temperature very quickly. So we've added an exhaust flap actuator onto the engine system itself. You can see one of those on my wall right here. That acts as a choke on the engine. It closes down, causes back pressure in the engine, and that increases the exhaust gas temperature to get our SCR chamber up to efficient operating temperatures. By law, all manufacturers that use SCR now have to have a diesel exhaust fluid quality sensor on the engine. That's because the ammonia that's in the DEF has a shelf life. If you store the DEF at a high temperature, the ammonia wants to bleed off and it will start to lose concentration. So you take that and if you work in conjunction with the oxides of nitrogen sensors that are on the tractor or on the engine. It used to be that at Tier 4A we had one on the end of the exhaust stack. Now we've added a second one in front of the after treatment system. So I think you all know what's coming next. If we know how much oxides of nitrogen we have going into our treatment system, we know what the results are coming out, and if we know the concentration of the ammonia in our diesel exhaust fluid, then we can predict and calculate exactly just how much DEF needs to be injected into the system to get the job done. So that's an efficiency that we're looking for too. We want to use enough DEF to get the job done, but we don't want to use too much because of the cost of that component as well. One more time, just putting these two systems side by side, your SCR only system on the left and your EGR based system or hybrid system on the right. So the takeaways from this one, if we're going to sum this thing up and put all these attributes on one hand, number one is that we're environmentally responsible here. You know, we have consistency in the operation and solution moving from Tier 4A to Tier 4B with SCR only. It's a refinement of that solution. We've kept it simple, and that's smart. No matter what you're talking about, simple wins. We've maintained or gained engine performance levels. So when you're finished over here with the theory, you're going to go over to the dyno tent, and they're going to spin a 4A engine and a 4B, and they're going to show you the difference in performance that is realized. And we have our fluid efficiencies. We're talking about the consumables in the engine: diesel fuel, the DEF, diesel exhaust fluid, and the engine oil. Now, we're more efficient with the fuel because we are burning it at a higher temperature, so we're extracting more energy out of the chemical energy that's put into the engine. With the diesel exhaust fluid, we have patented algorithms that are being read by those oxygen sensors and helping to calculate just how much DEF needs to be injected in there. So we're trying to minimize the amount of DEF. And we even talk about engine oil. With our clean burning engines, we have 600-hour recommended oil change intervals. None of our competitors go that high. Some of them can get 500 hours if they use premium filters and premium oil. But there are a lot of them out there that are 350 hours with fleet service. So when you're talking about a big high horsepower diesel engine that uses 5 or 6 gallons of engine oil, if you can prolong, you can extend those change intervals, it's going to help with the cost of the oil and the filters as well, and with the downtime to perform that service. So that's a real quick run through. We could spend the rest of the day into the weekend if you want to, but at this point I'll entertain any questions that you might have.